Hello and welcome to part 4 of the video series on vector analysis. We'll start by looking at the del operator, which is key in defining gradient, divergence, and curl of a scalar or vector field. The operator, which is also known as nabla, is equal to the partial derivatives in the x, y, and z directions. If phi is a differentiable scalar field, then the gradient of phi, which is equal to del phi, returns a vector field whose magnitude at any given point is the maximum rate of change of the field phi, and whose direction is pointing in the direction of that maximum rate of change. If phi is a surface of constant value, then the gradient of phi is normal to the surface at any given point. Sometimes we are interested in knowing about how a function changes in any specific directions. We can use the directional derivative to measure the rate of change in a particular direction at a given point. Now, if you look at this dot product and you have seen the previous videos in this series, you can notice that this is simply the way we computed the scalar projection of a vector onto another. This also tells us that the greatest rate of change of phi occurs in the direction of del phi, or the gradient vector, since theta will be 0 and both vectors will be fully aligned or overlapping. If directional derivative is positive, it means the function phi is increasing in this direction. Divergence measures how much a vector field diverges from a given point. This is an important concept in analyzing fluid flows, heat transfer, and it is useful in many other applications. A zero divergence suggests that whatever flows into a region flows out, so there is no net inflow or outflow of the vector field at the specified point. In other words, the vector field is balanced. A positive divergence suggests the presence of a source, for example, water entering a system from a pipe. A negative divergence suggests the presence of a sink, for example, water being drained out a system. The curl of a vector field measures the tendency for the vector field to swirl around, or its rotational effect at a point. The direction of the curl vector indicates the axis of rotation, and its magnitude represents the strength of the rotation. When the curl of a vector field is 0 at a point, it indicates that there is no rotational behavior in the field around that point. Let's see a vector field which is equal to minus y I hat plus xj hat. This vector field has a non-zero curl of 2 times k hat vector. The magnitude of the curl indicates the strength of the rotation in the field. The direction of the curl, which is given by k unit vector, indicates that the rotation is occurring about the z-axis. The positive sign of the curl indicates that the vector field introduces a counterclockwise rotation, which we can see in this figure. Now let's look at another example where the vector field is equal to x I hat plus y j hat. The curl of this field is 0, so there is no rotational behavior in this case. Also, as we discussed in the previous slide, this vector field is showing the divergence behavior. We can confirm this by computing the divergence of this vector field, which is equal to 2, and a positive value confirms the spreading out behavior at a point. Here are some of the key formulas that involve the del operator, and these are used frequently in the real-world applications. The figures used in this video are plotted using the Python codes we saw in the previous videos. Vector fields are plotted using the quiver method, and the dot and cross products codes are also discussed in the previous videos. We can easily use the code snippets from the previous videos and create an updated version to plot these figures. The only new thing is that we have used the NumPy's mesh grid functionality to compute values over a surface and on a 2D 3D grid. With this, we conclude our video. In the next video, we'll learn about vector integration. Please subscribe to my channel for more videos like this. Thanks for watching and see you in the next video.